Okay.
Yesterday's one is recorded and it's on the YouTube channel already.
Okay, awesome.
Do you know where to find that? No.
I was about to ask you now.
Just type in wiskunde skynat. Go to YouTube,
Wiskunde.
type in wiskunde skynat, and then you'll find there's a lot of channels on there, or not channels, but you'll probably find some. I don't have a lot of stuff on there for English physical science, but you'll go to HS grade, homeschool grade 12 physical science.
Okay.
If your Afrikaans is good, then there's lots.
Okay, thank you.
Right. In another experiment, the learners drop a brick A from a height of 8 meters. Okay, it's very important to do a little drawing, just to give you some perspective of what's happening here. There's a brick, and they drop it from a height of 8 meters. And after 0.6 seconds, they throw a second brick B downwards at the same height. So this is brick A. So this is dropped. So its initial velocity is 0. Then 0.6 seconds later, there's another brick B. And that they throw down from the same height. So the initial velocity, there is a value. And they hit the ground at the same time. Ignore the effects of friction and calculate the speed at which brick B was thrown down. Oh, there's various ways to approach this. We can say, let me see what is the easiest way. The first way to view or to approach the sum is basically to calculate the distance that A has traveled in that 0.6 seconds.
Okay.
And then take that time from there when it hits the ground. In other words, I throw down A first. Let's drop A for 0.6 seconds and then determine its height. And then determine how long it will take to hit the ground, because that's the time that B will take to hit the ground. Do you understand that? That's one way of doing it. The other one is to do a simultaneous solution, which I think it's harder. So we're going to do the following. We're going to start with A. And we want to know what is the displacement after 0.6 seconds. This is what we want to know. So we have its initial velocity of 0. We have gravitational acceleration of 9.8. Therefore, we're going to choose downwards as positive. And we want the time of 0.6 seconds. We want the displacement. So I want to know how high is it from the ground after 0.6 seconds. And I'm going to determine its velocity then. Okay, so which equation of motion can we use if we have all those variables? The one that we don't have is final velocity. Is that agreed?
Yes.
So we're going to use one without the final velocity.
So we can use the delta x equals VIT plus half AT squared.
Yeah. G delta T squared. You've got that Silver's calculator, don't you?
Yes.
And you know how to use that in order to calculate this. Oh,
yes,
you don't
you
need
showed
one.
me.
Sorry, you don't even need
Just
to.
show me that.
Yeah, I have to show you. Okay, we wanted time. Oh, sorry, we don't want time. If I wanted time, then you can use the Silver calculator. I'll show you in the next example how to do that. Okay, so we just want displacement, which is quite easy. This is just 0 plus half 9.8 and then 0.6 squared. So that's its displacement. It's like 1.764.
Yes.
So in other words, what we've got at the moment, I'm going to draw a new drawing. And then we've got A there. And then B, we're going to throw down at the same time now. So the displacement is 8 minus, so this is 1,764. So I'm going to do 8 minus the answer. And there's only 6,236 meters available for A. Is that true?
Yes.
So what I can do, I can now calculate the time it takes for A to reach the ground. If I get this time for that A reaches the ground, then I have the time that it took B to hit the ground. Agreed? Because 0.6
Yes.
seconds later, I've actually done it not the wrong way. I've just done it dumb. I could have just worked out the time A took to hit the ground and then subtracted 0.6. That would have been easier. Think about it.
I understand it the way you're doing it now. Makes sense to me.
Okay. But I've done it more difficult. Do you understand that? I've done it on a more difficult way, or a longer way. Let's say not more difficult, just a longer way. Okay, but we can continue.
Okay.
We can continue. I don't know why I did this. I could have just calculated the time it took for A to hit the ground and then.
But we don't have the final velocity, so we wouldn't, or would we, oh, okay, you could have used the same formula. Okay, never mind.
Yeah. Okay, well, let's do it this way and I'll show you how we could have done it another way. Now I want to know what time it takes to hit the ground from there. Okay. So I need the velocity there at where A is now, which is dumb. You see, that's the extra step, but I can calculate it. Velocity final is velocity initial square plus 2g delta x. Is that true?
Yes.
So the velocity final, where it's now at the moment, is 0 plus 2 times 9,8, and the displacement it had was 1,76.
4. Yeah. 0 squared plus 2,9,8.
And then that answer, I just do root of the answer. I get 5,88.
Yes.
Okay. So the velocity there is 5,88 meters per second. So this sum, I'm rebooting the sum and saying, look, I'm throwing A down at 5.88 meters per second, and it's going to travel 6,23 meters to the ground. And then B is going to be thrown down for 8 meters at an initial velocity that I don't know. And the time is going to be what?
The same.
The same. So now I need to get that time there. I need to get the time it takes A to travel that 6,236 meters, starting at 5,88 meters per second, and I don't have a final velocity. So I can say the displacement is VI delta T plus a half G delta T squared. So now I can work out the time. The displacement is going to be 6,236. The initial velocity is 5,88, and the time I don't know, plus half times 9,8 times square. So look at what I'm doing now. 0 equals half of 9,8 is 4,9 T square plus 5,88 T minus 6,236. T equals. Now you can use your calculator. Do you know how to solve the equation with your calculator?
Yes, I do.
So you know you go press mode and then you do the number 5 equation.
I just used the equal sign and then I typed the whole thing in and then clicked solve.
All right, you can do that. But this is a quadratic equation. So if you go to your calculator and you press mode, quickly press mode.
Yes.
And then number 5 on my calculator is equation.
Yes.
If you press that, you'll see that number 3 is a quadratic equation. Ax squared plus
Yeah.
bx plus c. If you press 3, it will give you opportunity to type in A, which is 4.9, equal, B is 5.88, and C is negative 6.236. I press equal, and it will give me a value of 0.677. See that?
Yeah.
Or I press equal again, it will give me the next answer, which would be a negative 1.877. And this is not applicable because you can't have a negative time.
Okay.
So now I know the time. This is nice for quadratic equations, especially when you're writing maths and they say solve x rounding off to 2 decimals. Then you fill in that whole formula, minus b plus minus the root of delta. You fill it, you write it, but you just type it in the calculator and it gives you the right answer. You don't have to type in that whole quadratic equation.
Okay.
Okay, so that's the time it takes for A to hit the ground from that position. So now I can work with B. So this is a long sum. I did it long. I could have worked out the time from the beginning and just subtracted 0.6. Okay, now B has an initial velocity we don't know. That's what we're trying to find out. It has a displacement of 8 meters. The G value is 9.8. And the time it takes is 0.6777. I don't have the final velocity. So I'm looking for equation again without final velocity. So it's that same equation. Delta x is VI delta t plus a half G delta t squared. 8 meters is the initial velocity, which I don't know. And the time is 0.6777 plus half of 9.8 times 0.6777 squared. So it's just 8 minus that divided. Okay, so I've got, just reset your calculator on computer. Eh?
Okay, yes.
So I'm just going to take 8 minus all of that and then divide the answer with 0.6777. Yeah. I have 8.448 meters per second.
I'm just typing mine in quickly. 0.6777 squared. What did you get?
8.48. So I did this. I just took all of this purple part, I worked it out. I took 8 minus the
yes.
answer, and then I divided the answer I got with 0.6777. Did you get another answer?
6777. I'm just retyping it. I think I typed in something wrong.
Yeah, I
And then
could have also
by...
left it that square. So if I do that, if I subtract those pink ones from one another, I get 5.7495.
Okay, I got the same answer as you.
And then I
Yeah.
divide with 0.6777. 8.4.
Okay, yes.
So that's the velocity. You don't have an answer. You don't have a memo or anything.
I do. Let me just go out here. It's on my laptop here. So this is for 4.3.
8.48. Look, there might be a small difference in because we've done, I think we've done a long method to do this.
They got 8.43.
That's a problem.
To 8.48. So they have that whole like.
Yeah. So there's a difference in the
Yeah.
memo as well, depending on which route we've taken.
Yeah, the answer does say like from 8.43 to 8.48.
Yeah. Okay. Awesome. Okay, so that's correct. This wasn't the shortest method. This was just a method that made most sense while we were reading the sum. We could have worked out the time it took A to reach the ground and then just subtracted 0.6 seconds of that and then reworked B.
So for that, you just would have worked out the whole time.
Yeah,
Like
you
the
could have,
whole
we could have
period.
done this. We said, look, A is dropped with an initial velocity of 0, 8 meters. What is the time it took to hit the ground? So you can say, okay, fine. Delta X is VI delta T plus a half G delta T squared. So we can work out the time. The displacement will be 8. Initial velocity is 0. And then we have half of 9,8 T squared. So let's do that. I'm just going to divide 8 with 4.9. You understand that?
Yeah.
And then take root of the answer.
So it's H divided by 1.8. And then
Takes 1,27775 seconds for A to hit the ground.
okay, yeah, I got the same
And
thing.
therefore B, the time B will take to hit the ground is less, is 1,277, I think it was 0,6 seconds less. Nah.
Yes.
So minus 0.6 seconds. And then I get 0,6777 seconds. Was that the same answer we got?
Yes.
So we're there now. And then we say,
Yes.
okay, fine. The initial velocity, which we're throwing B down, we don't know. We don't have the final velocity. We're not going to use that. We have the time, 0.6777, and we have the displacement of 8 meters. And this is exactly what we've done here.
Yes. Okay, I got you.
We've just done that. And that's much easier, actually.
It's faster as well.
Much faster, yeah. But I just didn't think of that when we did it. I just thought we were going to work that. I overthought this question. The question was much easier than I thought.
Okay.
Okay, but it doesn't matter. The memo has got both. Okay, we haven't done a momentum impulse sum. This is another projectile movement sum.
Okay.
Another work energy. So maybe we should do the projectile while we're busy with it. A tennis ball is thrown with a velocity of 10 meters per second vertically downwards from the top of a 20-meter high building. The ball bounces off the ground, reaching a height of 1 meter below the point from which it was projected. So it will move upwards 19 meters, 1 meter below. Ignore air resistance and lateral movement. Okay, explain free fall. It's just a bit of theory you have to learn. It's got to do with the fact there's no external forces on the object. Calculate the magnitude of velocity with which the ball strikes the ground, 3.2. Okay, that's not difficult. That's the final velocity. Huh?
Okay, yes.
We have the initial velocity. We just need to make a decision. I'm going to choose downwards as positive. I always do if I can. If downwards is positive, then there's a positive 10 meters per second downward. Then G is also positive. If you make upwards positive, then your G value must be negative. Which is
Okay.
and your displacement will also be negative then. But everything is positive now. So I want to know what the final velocity is. I don't have time. So this is just
Okay.
V
Oh,
final
so you can
square.
use, yeah, you can use the VF squared equals VI squared plus 2A delta X. Yeah.
Some books use delta Y. Don't worry about it. You can use X or Y. It doesn't matter.
Okay.
So it's 10 square plus 2 times 9,8 times 20. That's not difficult, son.
Yeah, that's not too bad.
Times
2, 8, 20.
The final velocity is 22,18.
Yes.
Okay, you need to get, if they ask speed, you don't need to give direction, but they ask velocity, so you need to give a direction. See if there's anything difficult. Yeah, it doesn't Calculate the time it takes the ball to reach the ground after it was thrown. That's easy, huh?
Yeah, because now we have the final velocity.
Yeah, so now you can use a Mickey Mouse formula. You can use VF equals VI plus, what's it, G delta T.
Yeah.
I don't even ever use that equation now. I can't remember when the last time I used this. 22,18 equals 10 plus 9,8 times T. Okay.
So it's 22,18 minus 10 divided by 9,8. 1,2.
Calculate the magnitude of velocity with which the ball leaves the ground after the bounce. What's the velocity at which it leaves the ground?
That would be the final velocity, wouldn't it?
Well, I would start a new movement as the upward movement, where it leaves the ground with the initial velocity. It reaches a height of 9 meters at a final velocity of 0, because that's the maximum height. This is what we want. So we have displacement, 19 meters. We have G, which is 9,8. And we don't have time. So we're going to use a formula without time. It's that one again. VF square is VI square plus 2G delta X. Okay.
Okay.
So I'm using that upward movement as a whole movement on its own. It starts with a velocity I don't know. It ends with 0. And then, oops. Plus 2 times 9,8, very important, negative 19. Because the upward displacement is negative. So I'm just going to do 2 times 9.8 times 19 and do the root of that answer. And then I get 19,3.
Mine said error.
Yeah, but you probably typed in a negative 19.
So I only typed 19.
I typed in 2 times 9.8 times 19. Because
Okay.
I'm throwing this over to the left-hand side of the equation, eh? So that 19 becomes a positive.
Okay, I understand.
You just add that negative in your root. That's why it's giving you an error. So that's 19,3 meters per second upwards.
Okay.
So is the collision elastic or inelastic?
Inelastic because it's not conserved.
The kinetic energy is not conserved, yeah. So it can be inelastic if the momentum is conserved. But if the energy is kinetic energy or energy is not conserved, then it is not elastic.
Because it has to be momentum and kinetic energy, hey?
Yeah. It won't be momentum if it's not kinetic energy. If kinetic energy gets lost, then momentum also gets lost. Remember, because the momentum is directly proportional to velocity. So momentum, P, is mass times velocity. If the velocity changes, the momentum will also change. And kinetic energy is half mv squared. So if that changes, the kinetic energy will change.
Okay.
And the momentum will also change. But momentum is allowed to change. It can still be elastic if momentum changes.
Okay.
Right. What else is there? I've got this. This is a work energy sum. I think we need to do a momentum one somewhere. This. Okay, students are performing an experiment in the lab. There's a 0.9 kilogram trolley that's traveling at a constant velocity of 2.4 meters per second along a frictionless track. When a metal cylinder of a mass m is dropped vertically onto the trolley, The trolley with the metal cylinder continues to move at a velocity v shown in the diagram. Now this is an evil sum. Why? Your momentum sums are normally a trolley going in that direction and then bumping against or crashing against the trolley going in that directions. So this is called linear momentum because both are traveling in the same direction or linear to one another. That little mass piece is not linear. Okay.
Okay.
Let's interrupt this sum and just do linear one and then come back to this one. So if I had a trolley, and it has a 3 kg mass and it's moving in that direction at 4 meters per second. And now there's a little metal block traveling in that direction. And its mass is, say, for instance, 1 kg, and it's traveling at 3 meters per second. Let's get another value. I've got a 3 already there. Let's say it's traveling at 2 meters per second left. This is before the collision. So this is before. Then after the collision, let's say the 3 kg block. Now I can't give you that mass of that little block. Then you have everything. The mass is unknown. No, I can't give you the mass. I must just leave out something else. 1 kg. Afterwards, the 3 kg trolley is moving in a certain direction we don't know. And the little metal block M, which is 1 kg, is moving to the right at, let's say, what? I don't know. Let's say 3 meters per second. What is the velocity of the 3 kg block afterwards? Then you would have done the sum of the momentum initial or before equals the sum of the momentum afterwards. And then we'll do that the mass times the velocity of the 3 kg trolley plus the mass times the velocity of the 1 kg trolley equals the mass times the velocity of the 3 kg plus the mass times the velocity of 1 kg. Is that correct? Because momentum is mass times velocity. So right at the beginning, we have a 3 kg trolley. And let's use the movement to the right as positive. So it will have a 4 meter per second velocity. And then we have the 1 kg trolley moving to the left. So it's -2. That's great. Agreed.
Yes.
And afterwards, the 3 kg trolley is moving in a direction we don't know, at a velocity we don't know. So I'm just going to call it 3v. And then plus the 1 kg trolley is moving 3 meters to the right, which is +3. So on this I have 12 minus 2, which is 10. And this on this side I have 3v plus 3. So therefore it's 7 equals 3v. And then 7 divided by 3. 7 divided.
2,33.
So the velocity is 2,33 meters per second to the right. Okay, this was fairly easy. You could have done something like this.
Yes.
You could have done it if this little mass block is stuck onto the 3 kg, if they're stuck together.
Yes, a specific formula you use then. It's you times the masses, I think. You add the masses times the single velocity.
Then the right-hand side of the equation would have been 4v, because they're all both together.
Okay.
Okay, but now we have something different. Now we have a block not moving linear. It's moving in a totally different direction. They're not moving linear with or parallel to one another. So now it's slightly different. This is difficult. Not difficult, it's just like, I don't know, it's not a good example. Okay, we've got the mass, it's 0,9 kg. We have its velocity and it's traveling constant velocity along a frictionless track. there's a metal cylinder that's dropped on top of it. The trolley with the metal cylinder continues to move on. So the metal cylinder is now attached to the trolley. Use the graph to determine the magnitude of the velocity of the trolley after the metal cylinder is dropped on the trolley. This is interesting.
Okay.
Well, this is obviously before, and the green part is after.
Yes.
5.1.1. Well, velocity is displacement over time. You could have used this. Vf equals Vi plus, no. I can't use the G formula. I can't use any G or A's because I don't have acceleration. No, I could use this one. I can say displacement is Vi delta T plus a half G delta T square. So the displacement is Vi delta T plus 0 because there's no G or A value. But that's just the same formula as I've used there because I'm just dividing the T away.
Okay, yes, see.
Okay, so basically that's a gradient. It's gradient.
Yes.
So that is, let's use the Y values. It's 10,2 minus 4,8 over 5 minus 2. You understood what I've just done. And if they say
Yes.
use the graph, you have to use it as a gradient in a gradient method. So I've just done the change in, this is 5 and 10,2, that coordinate. And this coordinate here was 2 and 4,8. So I did y1 minus y2 over x1 minus x2. Can you see that?
Yes.
And that gives me 1,8. So that's the final velocity.
Okay.
That's the velocity after the metal cylinder dropped on the trolley. Okay.
Okay, so that's afterwards.
Yeah. The first blue part must be 2,4. Because that's what they tell you. So the velocity of the
Yes.
first blue part is 2,4. It's 4,8 divided by 2, which is 2,4. And then the velocity afterwards is 1,8. So the velocity here equals 1,8 meters per second. And the velocity here is 2,4. Good. So now I use the law of conservation of momentum. No? The law of conservation of momentum is a consequence of which Newton laws? Oh, that's an interesting sum.
It's the Newton's third law, I think. No. Newton's second law.
Why?
That's
I haven't seen this question ever, like in ever.
hold on. I know why. I was doing this morning.
Okay, so
Let me
P
see
equals,
where I put it. Okay, because it says Newton's second law in terms of momentum, it's the net force acting on an object is equal to the rate of change of momentum. So that's why it's his second law.
just want to work out something.
Okay.
So the force is kilograms times meter per second to the power of minus 2. That's F net. So what is P? P equals kilograms mass times velocity. Velocity is meters per second. So I check something. Yeah. If you differentiate this, you'll get Newton 2. So you're correct. It's Newton 2. Good. I just didn't know that. I had to quickly calculate it.
It's one in the IEB SAGs, the subject assessment guidelines. It's one of the definitions we have to know for heart.
Really? What's
Yeah, we have, I think,
definition of what?
it's a definition of Newton's second law of in terms of momentum.
In terms of momentum.
Yeah.
Okay. If you differentiate the momentum formula, you'll get the acceleration force formula. Differentiating momentum gives you Newton 2.
Okay.
Can you do some calculus? Yes, you can.
Yeah.
So I have P equals kilograms times meters to the power of minus 1 second. If I differentiate that, I'm subtracting 1 off that exponential value. Then I get meters times second to the power of minus 1 kg. And that's Newton.
Okay. Exactly what you
But
did.
you just learned that formula or that definition. I haven't seen that definition. I can't remember.
We have about like 6 pages of definitions.
Awesome. Really? Maybe you want to forward that to me. So I want to check if there's anything there that I've like that one. I'm pretty sure it's not part of CAPS.
I have no clue.
Hmm?
I have no clue, but this, yeah, I'll just send it to you.
Yeah, whenever you have time. Okay, calculate the mass of the metal cylinder. Okay, the sum of the momentum at the start initial is this equal to the sum of the momentum final. You can also write there before and after if you want to. Just initial or final, before and after. So right at the beginning, I have the following. I have a trailer. Okay, I'm just going to write mass times velocity equals mass times velocity. Now, you can include the little metal cylinder at the beginning if you want to, but because its movement is not linear, you are just going to ignore it. So I have a 0,
okay, can you repeat that?
Okay, 2,4. Right, in the previous example, the metal cylinder was moving linear to that trolley. So we added that. But this metal cylinder is not moving linear. Remember, it's a law of conservation of linear momentum. So the two objects must move parallel with one another or on the same plane. This little metal box is falling from what? Falling at an angle of 90 degrees to the movement of the trolley. So that is not part of your linear momentum calculation. So the mass of the big trolley is 0,9 kg and its velocity is 2,4. I'm using to the right as positive then. Plus 0, because that little block is not moving parallel or linear to the trolley. Then the mass at the end is the mass of the trolley plus the small block. Because now they're moving together linear. Now I'm adding them. And they're moving at a velocity of 1,8 meters per second. So now I'm just going to divide the 1.8 at the other side. So 0.9 times 2.4 equal, divide the 1.8 away. Then I get 1,2 equals 0,9 plus little mass. And then 0,3 kg is the value of the mass or the little block.
Okay, I see what you did.
And then they spoil the whole sum by asking, why is the vertical velocity of the falling metal cylinder not taken into consideration?
Okay.
So now they're just telling you, hey, you should not have used it. If you've
At least that helps for people when you like to see that you've made a mistake.
Yeah. And the reason it's because it's not the movement of the small cylinder is not linear to the movement of the trolley. The conservation of law of momentum is for linear is when objects move linear to with one another. I think my English is a bit bad there, trying to explain
Oh
that.
no, I understand perfectly.
I would like to get the proper wording, but I don't have it.
The movement of
The
the
movement of the falling metal
of the
cylinder
block
is linear to the movement of
is
the
not linear and therefore not in the same plane as the trolley.
yeah, therefore we can't take in consideration. What else do we have here? There's another one. Do you want to do another momentum sum, or are you actually fine with this? We can.
You can do another one.
Okay. I have a cool one somewhere. Let me just find it. Prelim, Gauteng. This is 1 year they had a difficult paper there. Okay, this is a bad sum, I think, if I can remember correctly. Just wanna copy it. Gonna make or copy the drawing as well.
Okay.
This is stunt dummy or something.
Oh, cool.
So they've got like a pendulum concept. There's a rope attached to like a stunt dummy. It's 5 meters from the ground, and then it swings down and then falls on top of a 60 kg wagon. So a 50 kg stunt dummy is attached to one end of a 5 meter inelastic light rope. The other end is attached to a fixed point P. Gets 5 meters above the vertical of the ground. The dummy is pulled upwards to point A, blah, blah, blah. When released, the dummy swings downwards along a dotted path on the reaching of the stationary wagon, not a station wagon. So the velocity is 0.
Okay.
The stunt dummy detaches from the rope, falls flat on the wagon and sticks to it. The wagon has a mass of 60 kg. The wagon and stunt dummy move as one unit towards the right. So it's a 60 kg wagon, and what's the mass of the stunt dummy? 50 kg.
50.
Genau. Calculate the magnitude. Let me copy this. It's a lot of sums here. We'll do them one at a time. Calculate the magnitude of the velocity of the stunt dummy when it reaches the lowest point B. 4 marks. So what would the velocity be as it just reaches B? And I mean, how would we do that?
Wouldn't the initial velocity be 0?
Yeah.
So then we use the equation of motion.
I'm just trying to find out if they're actually limiting us. State, calculate the magnitude. No, they're not limiting us at all. I'm just not 100% sure. Okay, normally, if they use energy principles, you're not allowed to use equations of motion, but they didn't say anything that we can. So what are we going to do? V is VI squared plus 2G delta X. Okay, good.
Yeah.
So the final velocity square is 0 plus 2 times 9,8, and the distance is 5 meters, eh?
Yes.
Okay, just be careful. Even though it swings at a curve, that is just 5 meters. So that's 10 times 9.8, which is 98. The root of 98. It's basically 9,9. If they've asked you to use energy principles, how would we have done it? Energy principle. You must use energy principles. In other words, if you use equations of motion, you get 0 marks. I would be using
Let
principles.
me look.
Pardon?
I just want to look at my formula sheet. Energy principles, work, energy, and power. Okay. And we need the velocity.
You can use the mechanical energy at A equals mechanical energy at B. You can use VNC, each change in kinetic energy plus change in potential energy. You can use V net equals the change in kinetic energy. The top one does make more sense. But I'll show you how to use it, because they normally limit you. They don't want you to use equations of motion in because you will have a whole question where you use that. So they'll try to force you to do energy principles. So mechanical energy at A equals mechanical energy at B. That's the first one. And mechanical energy at A. Have you done this recently?
The
Principle or law of conservation of mechanical energy.
oh yes.
So mechanical energy is kinetic energy plus potential energy.
Yes.
So that is half mv square plus mgh equals half mv square plus mgh. So let's do it the following way. I'm just going to divide with m right through because the mass of the puppet or the thing stays the same. Okay, so at the beginning I've got 0 because I've got no movement. And then I have the mass, which is deleted, or G times H, which is 5 meters. Well, I can just say 9,8 times 5. 9,8 times 5. And at the end, at B, I don't know the velocity. Plus, I don't have any height, it's 0. So now multiply with 2 right through, then I get 98 equals V square. So V is also 9,9 meters per second. Same as that sum.
Okay.
Or you can use VNC if you want to, or V net.
I like this, the mechanical energy of A equals mechanical energy of B.
But don't use it if there's any friction, or external forces.
Okay. But there is friction in this question.
Yeah, but not while it's swinging from A to B.
Okay.
So you want to stick to this method. You don't want to worry about the others. Yeah. Okay, fair enough.
Okay.
So I'm going to delete this one, because it's very likely that you'll be forced to use energy principles in an energy sum. Or, yeah, the sum was designed to test you on energy. So it's just,
okay.
They just left it out. But you are going to be forced to use energy principles, or the chances are really good. Okay. Next question. As the dummy and the wagon move as one unit towards the right, a constant frictional force of 60 newtons acts on the wheels of the wagon as shown. State the principle of conservation of linear momentum. So now they're helping you basically to tell you which formulas you're going to use in the next sum. We're going to use the conservation of linear momentum. There is a big problem, however. And that is that there's friction now. Understand?
Okay, yes, I understand.
Calculate the initial velocity, yes?
Don't we just work out the F net?
Yeah. We can.
Okay.
It depends on what they ask. Calculate the initial velocity of the dummy and the wagon soon after the dummy lands on the wagon. Not soon after, immediately after.
Okay.
So there's no, I'm not going to calculate the friction now, because this soon after is wrong. It's not soon after. What is the initial velocity? What is the velocity of those two things together as the dummy lands on it? Then I can use the sum of the momentum initial equals the sum of the momentum final. Friction is going to kick in on that moment. But remember, as the dummy falls onto the wagon, it starts with the initial velocity and then friction slows it down. So I'm just going to mass times velocity plus mass times velocity. The one is for the dummy and the other one is for the wagon. So this one will just be 0. And then after the collision, I have the mass plus the mass times the velocity. That's the mass of the dummy.
Because it's one.
Yeah, because there's 1 unit and a wagon. So this is wagon and this is dummy. Because the dummy mass is 50 times 9,9. That is 110 velocity. 50 times 9.9. And I divide it with 110. 4,45. The velocity is 4,45 meters per second to the right. Make sure I've got. So I just want to make sure if I've got the memo yet. It would be nice. This is a prelim memo. This is question, I don't know. No, this is definitely not the right memo. I don't know if I've got the memo. Question 2. They get 4,5 on the dot.
Yeah, when I put it in my calculator now, as I got 4,5 on the dots.
Oh, yeah. Okay, understand. The reason is you used answer times 50.
Yeah.
Somehow, okay, this answer here was 9,899.
So then it's like a little bit less.
But because it was a
9,9.
question, I rounded off to 2 decimals, which was 90. And then I used that 90 in my next sum. They just used the unrounded off value in the sum.
Okay.
Which gives them exactly 4,5. Okay, good. It's not a problem. It's not supposed to work like that. You're allowed to use a rounded off answer out of the previous section in your next section. But if it wasn't a question, you're not allowed to round off.
Okay.
You use 3 decimals or 2 decimals in IAB?
It depends on what the paper says as you start the paper. Normally it is 3 decimals, but it really depends on what they ask. Okay,
good. So if it was 3 decimals, it would have been 9.8999.
Yes.
Then the answer would have been 4.5. Then this would have been 9,899, and then we would have had 4,5 meters per second. Okay, we're almost finished. Then the next question is, what calculate the impulse provided to the dummy. What is impulse? Impulse is change in momentum.
Okay.
That's impulse, change in momentum. So what impulse is provided by the dummy? Well, you can say, what is the change of momentum of the trolley? Or what is the change of momentum of the dummy? It doesn't really matter which one you want to use. Okay, the mass of the trolley is 60 kg. And the final velocity is 4,5. And its initial velocity was 0. Right, what's that? 60 bracket.
60 times 44.5. 60 times 4.5. It's 270.
270. And then you use kilogram meters per second, which is same unit as Newton seconds.
Okay.
Again, they've got 269,98.
Oh, okay. So they.
Yeah,
okay,
but they used different. They said we're going to use the change of momentum of the dummy. The mass of the dummy is 50 kg. The final velocity was 9,899. No, I'm lying. The final velocity was 4,5 and then minus 9,899.
Yeah, that's
269.95 now.
yeah.
Negative.
Negative.
Yeah, I've got a mistake here. These two must be swapped around. No, it's not. The trolley is a positive change of momentum, and this one is a negative change of momentum. Yeah. The impulse on the dummy is negative, and the impulse on the trolley is positive.
So for the question they asked said provided to the dummy. So which one do I use?
The answer is negative 270 kilograms meters per second. So this is a mistake because we worked out the momentum is the same, but we forgot to change the sign because the dummy experiences a negative impulse to the left and our movement was to the right. So it was probably a better bet to work out the momentum of the dummy.
Okay.
It's the same answer. It's just different directions.
Okay, I understand.
Now calculate the distance by the dummy and wagon combined before it comes to rest. Well, what's the best way of doing it?
Hold on, I'm going to look at the sum now.
What do you want to? So let's just make a little drawing there. We're almost finished. There's the little system of the trolley and the dummy. The frictional force is 60 newtons. It's moving in that direction with the initial velocity starting at what? We don't need that initial velocity, do we? 4,5 meters per second. And the final velocity will be 0. Again, we should use energy principles, really.
Okay. So then you can use the same formula, the E mechanical.
You can use V net is the change in kinetic energy. Or you can use VNC equals what do you call it? Energy or whatever.
Yeah.
Energy. Do you write energy?
I just put an E.
Okay. So E equals the change in kinetic energy plus the change in potential energy. But this is a small problem, this formula, because there is a non-conservative force on the trolley, which is W friction, the work done by friction.
Okay.
So this other ones might be easier. So the work done by friction, that's the only force on it, equals what? The change in kinetic energy, half times mass times final velocity square minus initial velocity square. The work done by friction is the frictional force times the distance cos theta times half the mass, which is 110. The final velocity is 0 and the initial velocity is 4,5 squared. So now I have the frictional force of 60 over a certain distance, which we want to know, cos 180. Because the friction is left and the movement is right, there's 180 degrees between them. And that is just a half, that's 55 times negative 4,5 squared. So now I'm going to calculate the right-hand side and divide it with minus 60.
Okay.
18,56. See if you can get that. 18.
Okay, hold on. Divided by 60. Yeah, I got 18,56, but I still have the, yeah, okay, then it's the cos 180, which is 1, so that's 1, right?
It's negative 1, eh? So basically, it just makes the left-hand side also negative.
Okay.
So that's a maximum distance it's going to travel. You could have worked out the acceleration.
And then use
You
the
use
other.
F net, yeah.
Okay.
But that's not an energy. Yeah, it is. Newton is energy. So, yeah.
Okay, but this one makes sense.
Okay. Yeah, this does make sense. Okay, good. Excellent. I see you when? When is the next lesson?
I'm gonna check. Scroll up.
I have it on Friday.
Research. Yes, Friday, 9 to 10.
Okay. There's also homeschooling lesson for, there's someone else joining a lesson on Thursday, 10:30 till 11:30. Think about
Okay.
it, join, but that's going to be, I'm not sure what that person is going to want to do. It's probably not going to worry what we do.
Okay.
Just keep that in mind and let me know.
Okay, perfect. Thank you.
Keep well.
Okay, see you soon. Bye.